Welcome to another day of learning physics. I am Christian Dikpikunag and today, let us all learn about confinement. Upon hearing this word, we may get curious about how this word becomes related to physics. We may say that confinement is a situation in which an organism, like humans or animals, is kept somewhere, usually applying force. This time, let us try to relate how confinement became possible in physics. But before we proceed, let us first unlock terms that we will encounter in our discussion. First is quark. Quark is a type of elementary particle and a fundamental constituent of matter. Quarks combine to form composite particles called hadrons, the most stable of which are protons and neutrons. Next, hadrons. It is a composite subatomic particle made of two or more quarks held together by a strong interaction. Another is bosons. It is a subatomic particle whose spin quantum number has an integer value. Bosons form one of the two fundamental classes of subatomic particles. Next word is fermions. Have add half integer spin, and it follows the principle of Pauli exclusion. Next is Pauli exclusion principle. It states that no two electrons in the same atom can have identical values for all four of their quantum numbers. And last, eightfold way, an organizational scheme for a class of subatomic particles known as hadrons that led to the development of the quark model. Alright, let's start our discussion with a situation. Suppose you are asked to cut a bar magnet in half. What do you think will happen to the poles of the bar magnet? Will both halves contain two north and two south poles? Or will still have one north and one south pole on both ends of the half? A bar magnet in half, the magnet will still have a north-south pole on both ends. We will not get a north pole and a south pole separately, but rather, we will get two parts of a north-south pole or simply two magnets. This idea is the same as confinement. Matter, all the stuff that makes up the world, is made up of atoms. Atoms are made up of protons, electrons, and neutrons. They are made up of 3 quarks each. Electrons are elementary particles. They are not made up of further fundamental particles. But how do proton and neutron differ from each other? Neutrons and protons are not elementary particles. They are made up of further fundamental entities which are known as quarks. Neutron is composed of 2 down quarks and 1 up quark, while proton is made up of 2 up quarks and 1 down quark. Quarks are entities that make up a class of particles known as hadrons. Different kinds of hadrons can be organized or grouped as bosons or fermions. Bosons have an integral spin, while fermions follow the principle of Pauli exclusion. Many hadron particles experience strong attractions. There are a huge diversity of hadron particles, and one very natural question that comes is that, are all these particles elementary, or are they made up of further elementary particles? This question led to the idea of eightfold way, which is the arranging hadron particles into charge or groups or geometrical patterns based on the same spin but different charge or strangeness. Examples of these groupings are the baryon octet, which consists of 8 baryons lightest particles, all of them having spin half with different strangeness and charges. Meson nonet, with particles of spin 0, has different strangeness and different charges. Another example is baryon decaplet, which is a 10 baryon particle, all spinning 3 by 2, but with different strangeness and charges. These are just a few of the examples of these groupings. Recalling the periodic table of elements, which consists of more than 100 different elements or atoms, they are all essentially made up of electrons, protons, and neutrons in different combinations. Same with the diversity of elements. They can be created by recombining electrons, protons, and neutrons. However, there is one serious problem that may arise as a result of the organization of hadrons in terms of quarks. Many hadron particles consist of more than 2 similar kinds of quarks. Recalling the composition of neutrons and protons, neutron is composed of 2 down quarks and 1 up quark, while a proton is made up of 2 up quarks and 1 down quark. So how do these 2 same kinds of quarks exist in one subatomic particle? This violates the Pauli exclusion principle, which states that no 2 electrons in the same atom can have identical values for all 4 of their quantum numbers. With this, they suggested that maybe, apart from quarks being divided into up, down, and strange, there is some additional property associated with these quarks, which when they come together to form hadron particles, is in different proportion. And that additional property is known as Quark confinement. It is the phenomenon that color-charged particles, such as quarks and gluons, cannot be isolated, and therefore cannot be directly observed in normal conditions below the Hagedorn temperature of approximately 2 terakelvin. Experimentally, none of these quarks have been isolated and detected as individual particles that lead to quark confinement. Hadrons have 3 quarks that are very much attracted to each other because of strong interaction or force due to their color property. There is an exchange of particles going on between these quarks, which are known as gluons. Based on the exchange of gluons between these quarks, it leads to the creation of very strong forces. This strong interaction holds these quarks to be together inside the hadron particle. The nature of these forces is like a spring. When we pull the spring, the force extended increases. The more we try to pull the spring apart, the more the force it brings it back increases. In real life, the spring will break apart. But when we try to break the quark by giving some kind of external force or energy, we are trying to break apart a certain combination. Just like in the picture, where meson is being tried to break apart by exerting energy, instead of the quarks be isolated, we will end up creating antiparticles of quark or antiquark. For example, let us suppose that we have a neutron particle having one up quark and two down quarks. If I provide a huge amount of energy to the neutron to break it apart, what ends up happening is that the force is used to create quark or antiquark. The combinations of quarks will shuffle, creating two up quarks and one down quark, which will become a proton. And another is an anti-up quark and one down quark, which will become pi meson. Essentially, instead of the external energy breaking apart the hadron into its quarks, you end up getting a new particle. In other words, the quarks are just being rearranged or reorganized into a new particle. This is the same with the idea of magnets. Having a north and south pole, when we cut the magnet in half, we will not get a north pole and south pole separately, but rather, we will get two parts of north-south pole or two magnets. And that is all about quarks and quarks confinement. I hope you learned something from my presentation. Thank you very much for listening.